Okay, good afternoon, everyone. Welcome to DataEDGE, the 2017 edition. My name is Jonathan Starr. I'm going to be the host of the sessions over the next day and a half. I just want to tell you how impressed I am at the fact that I've been able to get up here and start talking just at 2 p.m. That's pretty impressive, and actually I've been running this for about 3 or 4 years, and it's the first time I've seen that happen, so please give yourself a nice kind of silent round of applause for that. As you are probably well aware, we're starting DataEDGE this year with 3 concurrent workshop sessions. And there's 2 going on in other rooms. This one is being run here, by far, I think, the most popular. So again, well done for choosing this one. I'll introduce in a moment Glyn, who will be running this session for the next hour and a half. So we'll run it until 3:30. We'll take a break, and then everyone who's in the other sessions as well will join us for the rest then of the plenary sessions for the rest of the afternoon, and we'll be in that format until tomorrow. So with that, I'm not going to delay this any further and just say I'm delighted to welcome here Glyn Durham. Glyn is the senior instructor at Cloudera, and I think previously worked in various roles, including instruction roles at Oracle as well. So with that, please, can you join me in welcoming Glyn this afternoon? Glyn, welcome.
Yeah, okay. Hello. So this presentation, tutorial really, I was given the title Introduction to Data Science. It's a broad with Hadoop, and they're both Hadoop and data science are broad and deep topics, so it's necessarily introductory in nature. But I did have a hypothetical listener in mind, and the question is, raise your hand if you just learned how to spell Hadoop. Okay, well then a lot of this will be remedial. And lower your hand if you can't, and raise your hand if you can list and explain 5 or 6 machine learning algorithms. Okay, so the hypothetical student would raise their hand the first time and lower their hand the second time. So I've got a lot to say about Hadoop, a lot of a drill down into Hadoop, and this will be interesting. If you know Hadoop, then maybe what that means, we'll be blasting through some of these topics. I want you to raise your hands and ask questions as we go. I won't be pausing for questions at the end. We're just going to go through. And so let's just keep it informal, bring questions. And you might help me in terms of the recording. If I forget to repeat or summarize your question for the recording, ping me, make sure I do that. So my name is Glyn Durham. I am with Cloudera. I've been with Cloudera for over 6 years. I teach all of the courses. I've been working with the technology for quite some time. And as we said, I came from basically relational theory into Oracle, into MySQL, and now into Hadoop. And if you're interested in data, then I think that this platform is a very interesting space to be in today. So anyway. These are the topics, short and sweet, quick summary of what is it we're about, Hadoop and data science, how does it fit. Really, this drill down into Hadoop, this part that will largely, I would expect, may be remedial for some of you, depending on what you know already. Like I said, I didn't get very many hands when you said, do you not know about Hadoop? And then specific focus on Spark, then looking at machine learning, and then trying to look at the future. And what I mean is the near future, like right now. What's happening now and what we're looking at the runway for I'd say the rest of this decade. So short and sweet, data science is gathering data, wrangling that into useful shape. That's cleaning it, joining different data sets, finding representations for data that are useful, and probably cleaning it, right? And then applying statistical programming and machine learning programs to that to gain insights, right? So really, in a way, data science is sort of the sexy buzzword for what I would say is a continuum with statistics. the idea is that you have all kinds of raw data that is not of a pure structured representational form like a relational database system, but it's just more like raw data from which you want to mine insights, usually using statistical programming techniques or machine learning, which is really just more of an algorithmic approach to fundamentally the same thing as statistics. Another way of saying what data science is the job title that Jeff Hammerbacher and DJ Patil invented when they hired new people into Facebook and LinkedIn, respectively, to do this job, to basically address these issues in the first data scientist hired in 2006 in Facebook. But anyway, so that's what data science is. And the acquiring data and data sets and the wrangling of data is, for good or ill, 80% or more of the job if you're lucky. If you're lucky, it's only 80% of the job. If you're not lucky, it's all the job and you don't have any time to do any really good productive analytics. So that's really the reality. So that's what, that's what data science is. Machine learning is, of course, these variety of techniques to gain insights from data. And machine learning as an academic pursuit is not new. This paper is one of the key insights that Andrew Ng acknowledges in terms of his appreciation for where we are today, where things have, what's the case, what we can do. And that is this paper from 2001 that basically brings forward some well-known machine learning algorithms to perform a task called classifiers. And what the paper shows from a series of tests is that the algorithms tend to, they have minor incremental differences in terms of accuracy that they gain, but that all of them gain with data, right? So that the application of a simple algorithm with more data is a winning combination, right? And, of course, coming up with another algorithm to gain even a minor or some niche circumstance where you can show some incremental gain in accuracy, of course, that's a good thing to get publications, to get tenure, right? But for applications, a simple algorithm and a lot of data is winning in the market today, right? And Hadoop is an open source software platform for gathering, acquiring, storing, and processing massive amounts of data, exabyte scale in a single Hadoop cluster today, right? And we've got customers today that are storing hundreds of exabytes across multiple Hadoop clusters in their enterprise, right? So, and it does it economically. It uses free open source software to do it. It uses sort of standard hardware configurations to do it, and increasingly more today also an option of working in the cloud or hybrid services where you want to store, whether you want to run Hadoop clusters on premises with your own hardware in a data center, or using cloud services, or combining how you use your data in one or the other, right? So it does it economically, and and so what we've got is this trend to the cost of compute falling, the volume of data available, and that leads us into the sort of perfect storm or the viable circumstance we're in today that makes machine learning really, it's just an explosion of machine learning applications today and more to come. So that's the short and sweet story, right? Data science is using data. There's data. You want to store it cheap. You want to work with it, right? But here's sort of a drill down into Hadoop. We'll talk for a few minutes about Hadoop. The word Hadoop originally was a child's name for that stuffed animal. That's the actual Hadoop. The guy called it Hadoop, actually. So Doug Cutting was on the project that developed this open source project, Hadoop. And when he was casting about for a name, his young son had this toy and called it Hadoop. And he took the name because it didn't mean anything else. It was easy to say and spell, and it didn't mean something else. But then really, and this is a cause for some confusion in discussions with people, something that's worthwhile trying to be clear when you're having conversations with people about what you mean when you use the word. Does Hadoop mean Hadoop core, or does Hadoop mean the Hadoop ecosystem? To be honest with you, I informally tend to think of it in the third use, the Hadoop ecosystem. But just for the sake of accuracy, one just wants to be clear with terms. But anyway, we're going to talk about Hadoop core for a little while. It's a free open source software project. It is managed under the auspices of the Apache Software Foundation. And their front door is the web page, apache.org. You will see references to the URL for an Apache project, and you will see the logo for an Apache project repeatedly through my discussion. So anyway, it was started in 2006, so just not quite 11 years old, and there were papers from Google in terms of their own internal data processing frameworks that they were using. They published white papers in 03 and 04, and those were the inspiration for an open source development that occurred with this open source project, this Apache project. Right? So basically, engineers worldwide are committing engineering or documentation, and you can file bugs transparently. You can follow it. You can follow the state of what are enhancement requests or bugs or feature requests. You can sort of see that all going on transparently on any of these Apache projects. And they're all Apache licensed, which means that it's legally allowed to use it embedded in commercial software for free.
Okay, ready for a second?
Yes.
Let's switch out your mic.
Uh-oh. Pause for. I might mention to you while I'm pausing that I am going to pause for 2 commercial interruptions. So most of what I'm talking about here is open source, just the open source world. But I will have 2 commercials about offerings from my employer, Cloudera, because I actually feel that it would be a disservice to you to not mention some of these offerings. I think they're very valuable in this context. So anyway, so Hadoop core is HDFS plus Hadoop MapReduce plus Yarn. Those are the software components of Hadoop core found at hadoop.apache.org. So that's the original platform, right? So then what is HDFS, Hadoop Distributed File System, is a simple file system, right? MapReduce is a scale-out processing framework, and Yarn is a resource scheduler. We'll start talking about all those in a little more detail, right? So the basic question is that I have this large entity, if you will. A cluster today is like the mainframe of yesteryear, right? I don't see a whole lot of gray hairs in the room, but I mean, there are those of us who remember submitting batch COBOL jobs and RPG and things like that way back in the day on the mainframe, right? So really, what you've got is this large, big, powerful entity, right, that can store a lot of data and that can do processing on a lot of data. At least originally with the Hadoop project in batch. In other words, no interactive capability. You just basically can pour data into it, and then you can run programs that run in batch. Run the program, get a program running, go away, come back, and it may be in 10 minutes, it may be in 10 hours, it may be in 10 days, right? Come back, and that program has generated some new data set that you can then download and look at and examine and do useful, see if that's got useful insight, right? So basically, very simple functions. I want to save something in a file, I want to read a file or read part of a file, and I want to run a batch program on data in that entity. So HDFS is composed of, the way it's implemented is with a set of daemons, long-running background processes that run on different computers that are of course tightly coupled to make up your cluster, right? So, and a supervisory daemon called the name node. If you're into Java, it's a JVM running the name node main class. That's the class that it's running, right? And a supplement to that, I'm not focusing on that detail, but to avoid single point of failure, there's a redundancy there with a failover so that you can keep the thing up all the time. But then what you're fundamentally doing is you're scaling out storage of available disk across multiple machines. Here I'm illustrating 4, but we have customers that are running 4,000 of these machines, right? But basically, these machines, by virtue of running a data node daemon that's communicating with a name node daemon continuously over a network with heartbeats and commands, and calls going back and forth, these things are contributing their disk storage to a larger file system that is an abstracted file system across the local file system of all of these local machines, right? So the file system HDFS, it's a POSIX-like file system, meaning it's like Unix or Linux. You've got /separated directories and files. But if you write this file, so this user of Hadoop writes this file, what they do is, so I want to write a file, they get a path, composes a path, and the name node determines, oh, well, that file is going to be made up of different pieces called blocks. The size of a block is configurable, default is 128 megabytes. And so then the process starts writing that file, and it writes, say, in this case, say part 1, and it writes it, it sends it to a data node, which sends it to another data node, which sends it to another data node. Those are concurrently writing to disk and then responding back that they succeeded, right? So what you get is an immediate, synchronous, redundant write of the same file in 3 different machines. The same piece of the file, up to 128 megabytes, and then when you get to the next piece of the file, do it again, another 3 blocks somewhere else, and then when you get another 3 blocks somewhere else. If, say, it was a 2 terabyte file, you could think it through. That's 16,000 of those, 16,000 blocks, each replicated 3 times. Replication count is configurable, but 3 times seems to be a sweet spot. Obviously, higher would give you more safety, but it would sacrifice capacity, right? And lower gets to be more risky, right? And the file system is self-repairing. So in other words, these data nodes are continuously heartbeating to the name node, and if a data node fails to heartbeat in after a configured timeout period, 10 minutes is default, then the name node will say, well, all those blocks are lost. Let's order the remaining living data nodes to re-replicate the lost blocks so that there's going to have reliable file storage. This is a battle-tested, road-tested, battle-proven technology that stores, as I said, in a single coherent file system. Oh, gee, let me pull out in my back pocket of this USB drive. I will say 100 petabytes. 400 petabytes, right? Moving into exabyte scale, subject to the number of machines you give it. So obviously we can work with technologies where Hadoop is, what Hadoop is for is when the data that you have exceeds what you can economically do on one server. So some say 30 terabytes, maybe, I don't know, amounts, sizes of disk keep changing today and the cost of disk. But basically, when you get into 300 terabytes at that point, what are you going to do? Right? So that's what this thing is for. It can store out to much, much higher capacity of storage. To read a file, then the API, the program that wants to read a file, just using the API, and it transparently interrogates the name node to find out what are the pieces of the file, and then it gets any one of these copies, any of these replicates of a block is a legitimate copy of the file. So basically the reader will actually be offered by the name node the most convenient, that is most proximate machine to read that block from, and then the next and the next. Or if which is commonly the case, if the reader wants to read part of a file. So again, imagine a 2 terabyte file, but you can say, well, what I want to do is I want to read that 2 terabyte file from offset, maybe 480 megabytes plus 480 megabytes plus 128, some offset. Then it can just read one block and not have to read the whole file, right? So what we're looking at is safe, reliable, scalable, sequential write and sequential read. massive files. And what does the structure of the file have to be? Well, there's a rule that data has to meet to be stored in HDFS. It has to be data. That's the only rule. So there's no restriction whatsoever on file format or contents or what it is. So structured, unstructured, semi-structured, whatever it is, you just dump data into this thing. So that's why some people call it a data lake, right, or reservoir, right? And so so then there are dozens of commands. This is just to name a few commands that sort of are available to write files into HDFS. So this sort of like a client that's on the edge of the cluster can just do that put command and takes that source file and makes a copy of that in that write file, like an FTP put, right? Or fuse is this sort of kind of janky little hack where it basically pretends to mount HDFS as if it were just another a storage device on your local server. So then your shell commands just CP and MV and they just operate. So, oh, this directory over here is my 100 petabyte partition, right? So you just copy files and read back. Right. Question?
From the previous slide, just one question. When it splits it up into the various places that it stores it, is there some optimization around sequential pieces being stored on the number of pieces is really large, so that in case your example of getting one chunk out, you make sure that you're providing the minimum number of distinct data nodes in order to get the file.
Okay, so I think I can interpret your question as a question of the block placement policy. Does that sound right to you? So that's the term we float around. So what's the block placement policy? Well, that's handled in the name node. It makes the decisions. It doesn't actually handle data, but it directs the placement of data. It directs the metadata, what are the directories and what are the placements of blocks. And then it directs where the blocks are stored. And basically what you want is, for reasons that we'll see later down the line, is what you want is dispersal of your file across all the storage of your systems. But what it basically does, and then with a little bit of a twist on that, I'll talk about that for a second, is that if the writer is running on the same machine as a data node, right, then the first replicate of a block by the name node is chosen to be local on that machine, right? If the writer is not in the cluster, in other words, just a client to the cluster, then the name node selects any data node on the whole cluster that is less busy at the moment. So the name node has a continuing notion of how many I/O threads are in use or are pinned at the moment on all the data nodes, and it'll pick anything on the less busy end of the list, right? Anything, right? And then the second and third blocks are chosen off rack from the first block. So the second replicate is off rack from the first to give you added safety, so that if you have a top of rack switch failure and you lose a whole rack, you still don't lose the data. Data is still available at that time. And then the third replicate so you're picking a less busy node anywhere off rack from the first, and then the third replicate is some less busy node on rack with the second. So it's just you're spanning racks, but you're not going overboard with more racks. But as long as there's capacity on the local node and you're writing locally, you will write locally. So what's interesting about that is the complementary side of it is if you want to read data, if you want to read a file, then the name node will offer you, this guy says, I want to read this piece of a file, and the name node says to it, what you need to do is you need to go request that data from this data node or that one, and it will give it an ordered list. Try this one, and then try that one, and then try that one, and it will put the first one most proximate to the reader, so that if the reader is local, you'll read local. So what that means is a program that's running on the cluster on one of these are called slave nodes or worker nodes, right? So if a process is running on a slave node, it writes the file with replication for safety happening at the time, and if it wants to turn around and read its own file, it reads local. See what I mean? It's kind of interesting, combination. Yes? I'm sorry?
The example here, every chunk, part 1, part 2, part 3, they're done independently.
So each block, the block placement policy that I just explained to you is repeated for each new block as you write your file sequentially. Right. Yes?
Are the block placement policies
Yeah, so the question is the block placement policy published? So there's a book on O'Reilly written by Tom White, a Cloudera employee, called Hadoop, The Definitive Guide. And that book is an amazing piece of work. When I joined the company over 6 years ago, I had to stop and sort of tap him once in a while and say, Tom, you did it again, you did it again. He remotely travels to, he does mental telepathy. He remotely travels to where you are. He reads your mind, thinks about a question, reads your mind about a question you have. Then he does time travel and travels backwards in time and writes a book answering your question. So it's just amazing. The deep dive into the technical details is in there. It's not really a tutorial, but it's an excellent reference. Hadoop, the definitive guide. Yes?
In the process, your data is replicated 3 times. How do you read the data faster or write the data faster? For example, can you read the 80% of it from the local and 20% of it from the remote?
Well, so reading, so there's an important really concept about reading. We want to be able to do distributed reads, and we're going to get into MapReduce, and that's going to be kind of dovetail into your question. Okay, so but basically you're looking at sequential reads, right? So HDFS will do, so like I said, a series of commands. We talked about, you know, these different ways to do reads and writes. There's a Java API where you write a Java program that has commands to open files, create files, read and write files, and so on. So you can build out any kind of app in Java. There's a server that exposes the file system via HTTP requests. So you can just issue curl commands to it if you want to do that. And this is just to name a few. As you might imagine, Cloudera has like something like 2,300 partners. So any kind of tool that touches Hadoop is going to have one or more commands to write data or read data. Right? So that's just very, very common. You just, you know, many options for doing that. So let's just summarize strengths and weaknesses. HDFS is good at storing enormous files. A 2 terabyte file, Hadoop does not break a sweat. A 20 terabyte file, a 200 terabyte file, it doesn't care. Right? As long as you have capacity, you have capacity. Right? It can store the data reliably. Because of the redundancy, the self-repair, it is reliable. Right? It is good at throughput on sequential writes. Basically, once you get the daisy chain going of writing, you're writing at the rate of sequential throughput on a disk. So it's writing to this disk while it's concurrently writing to that one, while it's concurrently writing to that one. So there's a little bit of startup latency, right? But then the write is just, you're just looking at the rate of throughput, of disk throughput to write, right? It's good at throughput on sequential read of a file. You're basically reading, you know, sequentially reading off disk. And it does have caching capabilities in the data nodes so that you can, if you read and you want to read that similar, something nearby in that terms of that file again, that you may benefit from a memory read rather than a disk read, not to mention file system cache on the servers themselves. Right? So there's always that good thing that happens with memory. It is not good at low latency random reads or writes. Low latency random reads. So you've got your 2 terabyte file contains 50 billion records, and you want to read one of the records, right? The best you'll be able to do is to like go into some offset into probably the beginning of a block that you know is before or nearly before that thing, then start reading forward till you find some sync point that you can understand what byte you're on, and then read until you find that record. So the latency is very punishing. It's not at all good at sequential reads. What about random writes? Can't do it at all. Once you write a byte into a file, you have written that byte into a file. You cannot change what is in a file once it's been written. If you have, yes, question. That's okay. This is a good question. This sort of kind of a little bit, you're hitting me on the side, but that's okay. Transactions, ACID compliant transactions, that is, I would say, a bleeding edge area of Hadoop that Hadoop is fundamentally not able to do, right? So your ACID compliant relational database systems, Oracle, SQL Server, you know, pick your DB2, whichever, you know, whatever, MySQL, which of those you want to use, PostgreSQL, whatever you want. Those things have an important semantic power in terms of the relational model, the foreign keys, and then the ACID compliant transactions that have a critical and important role to play in the world today. Right, and so they're not going away per se. The problem is that they're too expensive to store data at this petabyte scale, right? And they don't have the tooling to accommodate unstructured or raw data, right? So they just are like you got to get out of that SQL, that's the sort of powerful SQL mindframe, relational transactional SQL mindframe, until somebody hits with a really strong working project that does transactional. And there are people who are working on that. Splice Machine is a company, Phoenix is a project, for example, right? So good question. Okay, but we're now back down to a file system, just a basic file system, right? Right? So, but anyway, you can't update what you've written in a file because it's what it's doing is sacrificing that core capability in exchange for this scalable, reliable, inexpensive file system, right? So you have a 50 million records in a 2 terabyte file. You want to update one of those records. The only way you could do it if you're just working at this level is to read the whole 2 terabyte file and write a brand new 2 terabyte file that's one record different, and then delete the old one and rename the new one. Forget it. Yuck. You know, latency is horrible, right? So just really basically untenable, right? That is not a capability. On the other hand, the purpose for the thing in the first place was, remember, Google, who designed this technology originally, says, well, we're just going to crawl the whole web and download our own copy of the World Wide Web, right? And then we're going to run a batch program that grinds on that and does some quantitative analysis on the web to become the search engine that wins, right? You know, anybody remember Alta Vista? Right? I mean, that's what they did. They designed this technology to do that, to become Google, right? So anyway, all you do is you read through all that data and you just store it. You're not updating it. It isn't transactional, right? Back in the day, it took them 4 weeks to do one crawl and store, and 1 week to run the program, the basic Pagerank algorithm, right? So anyway, that was then. So that's HDFS. New topic, MapReduce, processing framework. So let me just sit here. So I know nobody said they didn't know how to spell Hadoop. Who would say they know MapReduce? Oh, okay. Okay. Well, then you guys can listen and keep me honest. You know, correct me if I make a mistake. Okay. So MapReduce it's a functional programming framework that says to run a program, you fit your problem, your solution, your program, your algorithm into a series of functions that then are handled for you by a framework, right? So the basic idea here is that you take a set of input records, and remember we're looking at batch programming, a set of immutable input data set of records. We're going to run a batch program that when it's done is going to give us another set of records. This is unchanged. This is the new data set that arrives, right, from doing the batch program, right? So we're going to write a function that will take one record as an input, and it's a stateless function. It doesn't have any memory of what was called, what its last call from before, right? It's just going to be a pure function that says you invoke that function with the argument of a record, and that function will return a list of records, 0, 1 or more records of its own, some new output, right? And you're just going to have the system is going to apply that function to all the records in your data set. Whatever function you write there takes its place in its role in the MapReduce framework as the map function. Right, so having applied that function to all these records, I get a new set of records, or you could say I have mapped that data set to this data set. Now this is intermediate, this is ephemeral, this is not something that you're finished with necessarily, right? But an important characteristic of those output records is that they are of a structure of a pair or two-tuple or whatever you want to call it. They call the first part of it the key, the second part the value. And you can think of the key as has a controlling influence on the way the records will be handled subsequently. So here I'm illustrating the keys as grayscale, right, on these things. So these are records, some records have the one key and others have another and others have another. So then what the framework does is to automatically, for me, right, reorganize the records according to key. That's called shuffle or shuffle and sort, right? So this is the same records brought forward into reorganization where they are grouped up by key, or rather they're ordered by key, if you will. Partitioned by key is a lot of ways of saying it, right? And then this affords me to write another function that operates in aggregate, right? So it can operate on a group of records that have the same key. So you can invoke this function, you can sum or take a mean, or you can, some kind of aggregation, right, on this function. And that function is called a fold function or aggregate function or reduce function. Right? If you know SQL, then all your sum, min, max, all your group functions, those are all examples of reduce functions. Right? And then the reduce function is invoked with those intermediate records, and then it has the option to emit 0, 1 or more records at any given time, for one function call. And just by basically stitching together this map function and this reduce function, right, is how the framework operates. That's fundamentally what MapReduce is. And let's talk about this. So here's an example of some functions. The hello world of MapReduce is word count. Give me an input of text and give me an output of all the unique words occurring with their frequency in that text, right? So in a class setting, we would do this with like a 4-line poem, and then we'd run it again with the complete works of Shakespeare, and then we would convince everybody clear enough that you could run it again on the complete content of Wikipedia. Right, the same algorithm, no difference, right? So the function is to read a record is, the map function says, and by the way, just because of the details of the way the API works, the input records are also treated with a key and a value. But I don't care about the key. The key might be a line number, but the value is a string of text. And so the map, only it does is to just parse out, just to piece out the words in a string of text, and then emit that word with the integer 1. That's all it does. For each line of text, whether it be every line in Wikipedia or whatever your input is, every line in Shakespeare. And then, so then the framework will, if you emit the word as the key and the integer 1 is the value, then you get all the occurrences of a single word gathered together in shuffle for you, right? And then the reduce function, all it does is just sum all the ones for any given word. You get a word the, and you get a bunch of ones for every unique occurrence of the, and you sum those up, and you spit out this the and that count, right? So the input to the mapper might be 2 records like this. An output would be a set of pairs like this, words and numbers, the number 1. By the way, I understand these PDF, this will be made available after the conference. So anyway, and so then the input to the reducer is, for example, the key, the, and all the values that occurred from the across the whole data set, right? And then the final output is just to sum those, and you put these unique words in their frequency. You do the same thing with a 4-line poem or all of Shakespeare. We do that in class, or you do it all of Wikipedia. It's just a question of hosting the data. Yes? Yeah, you don't need the input key. In this simple algorithm, you don't need it. It's just if you look at the Java classes involved, if you write Java MapReduce, the class of the input record is a 2-part class. So it could be null value. But algorithmically, you don't need it. Yeah. I'm sorry, I don't think I repeated the question, but fair enough. Right, yes?
what is a good indicator that essentially that I should consider Hadoop as an offload mechanism for my data warehouse?
Okay, so I'm sorry, I'm not parsing what I'm hearing. You guys may notice I have 2 hearing aids, and I'm not hearing you very well.
So I have a very large data warehouse.
Yeah, data warehouse. Mm-hmm. Yeah.
It's running okay, right?
Yeah.
So what would be the indicator that I should start considering Hadoop to improve my performance or to deal with the future?
Okay. Okay, so there's a question of, I'm doing data warehousing, and so when would I consider Hadoop? What's the issues with Hadoop? It's a good question, and let's hold that. We'll get into that when we get a little bit further. Okay, so anyway, I just counted words. We can easily extend that notion to things like weblog analysis. So basically, you know, capture every weblog event of every web server and every server farm on, say, you know, like maybe, I don't know, Google or something like that, right? Every web events. So you capture all those web events, and then you can basically aggregate them by IP address, and you get a frequency of, you know, hits or IP addresses. And of course, you could join that with something like a geolocator and find out what countries are trying to hammer Google right now. For example, or indexing, of course, you just read a document and you find all the terms you want to index, and then you pair that with the ID of the document, right? So then you invert that, put the term you're looking for, and then the document ID it is, and you just aggregate that. Here's a term, here's all the documents that have that term. Right, so you build an index easily, yes?
Very basic question again. From the example, where would you, at what stage of the process, would you do things like check for spelling errors or alternate cases for the words, things like that, that will also point to the same thing? At what stage of the process would you correct that?
Yeah, so the question is, what if you're trying, like, you've got sort of variants on records, for example, case or spelling or things like that. I would probably, if it's a record level transformation you're looking at, I'm looking at doing that in a map function. Right, most likely, most of the time, right? And you know, PageRank algorithm, Google's winning algorithm, named after Larry Page, was to basically look at a page, and basically you assign expressed very simply here, a little bit simplified, is to take every page on the web, assign it an initial weight, right? And then you basically, the page passes out in a map function to all of its outlinks, you assign its weight. So in other words, I have a weight of 20, I have 20 outlinks, I give each of them 1, right? So I'm basically emitting an outlink and a weight that I want to give it. So then the shuffle aggregates all the outlinks and their weights that are assigned, and you just sum those. So you add up those weights, right? And you iterate on that. If you keep iterating on that, what you get is a reorganization of the weights across the whole web that represent the topology of the pages. What's the probability that a drunken walk would land on that page, right? Based on all the links in and out, right? And an important page confers importance to pages that it links to, and so on, right? And this becomes a ranking algorithm for the importance of pages that lets you sort results, and which is why you like search results out of Google. Right, so it's basically taking the web itself to tell you what are relevant pages on the web, right? And it's a MapReduce program, right? So anyway, ultimately, you can't just do, you know, you can see, you know, you might say, well, boy, that's pretty primitive, Glynn. All you've got is a map function or reduce function. Is that all? Yeah, that's all, right? So you have to shoehorn your problem into that framework. It's not just anything you want. It's this. You've got to do this, right? But what you can do is chain things together. So in other words, the output of a MapReduce program, so-called MapReduce job, could then turn around and become the input of another MapReduce job. And that's when the key and value may have use to you and your algorithm. Or if you want to carry information that way, it's up to you. Right, that's a place where the, you know, having key value on your input may matter. But the way the framework works is that it runs this whole MapReduce program to completion and then stops, and then you basically basically schedule another MapReduce program to run this, to do this, and then stops, and then you run another MapReduce program, however many you need to get to ultimately chain together the functions you need to get the results you need. And then, of course, you'd be deleting these intermediate results unless you have some use for them, right? So why are we doing all this? Why are we shoehorning everything into this problem? Because it is a framework that operates at scale, right? The notion is that you take your sequential data set, you partition the data set into separate input chunks called input splits, not always done, but commonly done, equals HDFS block, right? And you schedule independently a worker program to read some set of data, apply the map function that you want to apply across the board of the data set to that, to produce this intermediate data, right, the result of the map, and you schedule those all independently in a distributed fashion across your cluster, however large. If it's a 2 terabyte file, 16,000 separate input splits, 16,000 independently scheduled map tasks. Because we're only doing a stateless function, we can schedule them in any order with any degree of parallelism we can muster given the hardware, right? So you got 100 machines, you'll get through 16,000 tasks in maybe, I don't know, I'll say 20 minutes. If you throw another few racks at your cluster and you get 200 machines, you probably get it done in 5 minutes, right? So that's 20 in 10 minutes, near linear scalability, right? Once you start scaling, right? But then this shuffle occurs, and this is the exchange of ephemeral data from every machine in the cluster to every machine in the cluster. Right? So this is expensive but unavoidable, right? It's called this shuffle phase. But it reorganizes the same records again into partitions once again, but this time grouped up by key. And now we can independently schedule once again these reduce functions, these reduce tasks across multiple machines. So when I say that you can schedule something, you can partition a problem space into independent sets that you can subdivide at will, and then schedule independently. That's embarrassingly parallel, right? That's the term. Maps are embarrassingly parallel. Reduces are embarrassingly parallel. Shuffle in the middle is expensive but unavoidable, right? MapReduce is good at processing big volumes of data. It can scale out it linearly as you add more machines. It can continue to completion. There's recovery components already in place where if a task fails, then the work that contributed is just rescheduled again, automatically, right? And it's not good at running any algorithm you can think of. You have to fit your problem into this framework to do it, right? And notably, it doesn't want to have shared state overall. It wants to have stateless functions, right, with no global shared state that's changing, right, that's available across all the tasks in place because they're being scheduled asynchronously in distributed fashion across all these machines. There's not a shared state there. That's actually, if you drill down into algorithms and algorithm design, that's notable, right? But anyway, but maybe you can get clever and carry your state in the fabric of that data that you're running through this thing, right? So if you study MapReduce algorithms, you see examples of that, right? But it doesn't run in real time. They're all batch jobs. All this stuff, you fire this thing off, you go away, come back, and it'll get, and find it done later. And maybe it'll be 30 seconds, maybe it'll be 30 hours. Depends on the capacity of your cluster and the amount of data you're processing. But it won't be 3 seconds, right? It'll be like 10, 20 seconds, even on its little toy system with just one machine, right? It's not real time. So anyway, Yarn, that third piece of Hadoop core, is A set of daemons, here we're sitting alongside the name node and data nodes, the file system, is this thing called resource manager, node managers, which basically is this, node managers are able to offer process space on these workers at any given time. So they'll offer up, you know, I'll give you a core and 2 gigs of RAM to work with, and now you want to run a program, go ahead and do it, right? And then the resource manager is just supervising that, right? So the idea here is that Yarn supervises the allocation of processing resources on a continuous basis for you, and then so then MapReduce says, well, I'm going to schedule, I'll schedule map tasks, where it'll be 16,000 map tasks and maybe, you know, 5 or 10,000 reduce tasks to get this job done, or whatever the chain of things that we're going to do all these functions, however many we're going to do, right? That's what Yarn is. And that's what Hadoop core is. HDFS, MapReduce, Yarn. That's what Hadoop core is. That's all it is. It is nothing else, right? But remember I said there's 3 definitions: a child's toy, Hadoop core, or the Hadoop ecosystem. So let's start talking about other open source projects that are added to add functionality. It just turns out that the Apache Software Foundation, that when they want to add major features to a platform to make it useful, they tend to be for, I guess I would say for it makes it manageable to create a separate project with separate teams that work on their own, that they invent these own projects, right? So this is another project on Apache called Sqoop. The word is a mashup, SQL to Hadoop. You just give it a command and say, here's a 1,000,000-row table in my Oracle database. I want to load that into my Hadoop cluster, get a copy in the Hadoop cluster. Why? Because if I want to do data processing on that 1,000,000 rows, I don't want to unintentionally issue a distributed denial of service attack on Oracle by hammering Oracle with, you know, 40 or 50,000 queries on Oracle because I'm running one job. No, I'm going to drag the data into Oracle, into Hadoop, and then process it there, process a copy of it there. And also people use Hadoop. Yes, question?
Yeah, just a quick question. It seems like go back to a couple of slides.
Yeah.
It seems like the sorting, they're in the middle of the process. It's like centralized. How do you scale that up?
So it's, yeah, I mean, it's a shuffle and sort is heavyweight, and it involves, let me give you kind of a little bit of a flavor, and then I will let you kind of run with it. So this is kind of a deep topic and would take a while to go into, time we don't have, but basically what you can say is that this guy has to sort and partition his little small data set. So he'll partition it. You're going to call for maybe 3 partitions. By the way, this is configured by the programmer. I want 3 of these. I want 50 of these. I want 5,000 of these. So he'll sort his little small data set into the 3 partitions, and if it requires ephemeral write to disk, read to disk, do a little sort, a little small set, and then do a merge sort to get it back out to 3 sets that are miniature sorted. And then this guy will fetch its partition from all of the contributors and merge all of those. Do you see how I'm going, right? So that's a bit of a flavor about what shuffle is. But make no mistake, shuffle is expensive, right? It's unavoidable in many cases, but it's expensive. By the way, before I stop, let's just mention, if all you wanted to do was read records, scrub them, and then render them out scrubbed, get the representation all right and get rid of the bad records, then you just do map and you don't do anything else. Right? You save shuffle, you don't do reduce. So you can have a map-only job, right? But obviously, the more complex your algorithm will lead you into chains, at least a MapReduce or even chains, right? Good. So, good. So, all right. So this is scheduling all these things, and so Sqoop will do import. It uses MapReduce under the hood to do it. It schedules multiple concurrent bulk reads off of the database to then concurrently, I'll read 100,000 rows and write them while you read another 100,000 rows and write them while you, to get it all done in some kind of parallelized way. And it can also export, flat file data into some other relational system, any RDBC compliant, any ODBC compliant or JDBC compliant data store. So people use Hadoop to do ETL for their warehouses sometimes. So where their ETL for their warehouse takes too long, they get Hadoop and scale out the machines, and so then the transformation layer just scales out and runs faster. So that's Hadoop in service to a warehouse ETL cycle, right? That's a way of thinking about some things. But anyway, another project. So you got to get data into your Hadoop cluster. One kind of data is your relational databases. Another kind of data is just files. We saw a few commands for that. Another kind of data, and this is really the common thing today, this is the era we're in today, is ephemeral event data. What Ralph Kimball, Mr. Data Warehouse, calls light touch data. A log event, a sensor, a tweet, anything spinning off of your smartphone device, Internet of Things, all that stuff, they're just emitting digital events on a continuous basis, right? So what you got is the continuous ingest. So Flume, named after the Flume log ride from Disney, which is named after the 19th century channels of wood with watertight thing. You transport logs, so logs go through the Flume. Get it? Right? So anyway, that's what it does. It's just these gray boxes are agents that are continuously listening for events and routing them forward, right, for ingest, right? And so it can listen to all kinds of events, and that just being spun off, whether it be logs or syslogs or socket events or Twitter feeds, or sensors. It can be customized. So all kinds of features there. Kafka, you may have heard of. What it is a reliable, durable data store that it allows you to write events to it in some order, and then has some guaranteed retention of that information for then reading it, picking it up and reading it later, right? So it can be thought of in some ways as a way of data integration between all kinds of systems and exchange of data. So in other words, rather than having to write a transport from a system to another and having this rat's nest of technologies to maintain, it's just, all kinds of technical debt, you have this very well-designed, well-built system that can absorb events, store them reliably, and then make them available to readers in a standard kind of API, standard calls, right? So that today you've got people like LinkedIn they're moving, I want to say, on the order of like 40 petabytes into Kafka every day and reading 80 or 90 petabytes out of it every day. So you can write it and then read it multiple times. Different readers can, of interest can read things. It's very interesting technology, yes?
Are there some measures that show that when you undertake Kafka, that it improves
performance? Performance of what? So the thing is
you're recalling data processing data. If it's nicely mapped, it's nicely organized like this, and you don't have the rat's nest you find recall.
Yeah, that's interesting. I don't think I don't know if I can speak to Kafka as a question of performance. So what it is it's a transport, right? And so people have built, message buses and transporting messages between systems, in the enterprise or the organization. That's not new. There's roll your own message buses, and there are dozens of them, but the issue is that as organizations grow and they add more systems and they grow more kinds of data, they keep incurring more and more problems and technical debt, in terms of how do you maintain, how do you write this new wire, how do you keep all these pipes. So what it is basically it's a standardization and simplifying your plumbing to get data between systems. Right? That's really more what it's about. It's about reliability. And it is performant in that once you write an event to Kafka, it becomes available for read on the order of 100 milliseconds, maybe. But it's really the simplification of the engineering problem of moving data between diverse systems is that it's addressing, I would say, rather than performance per se, and it's performant within the realm of what it's doing. If you just like Google for a blog, the log, what every engineer should know. just stop there. It's a longer title, but it's a blog. It's a really nice blog written by Jay Krebs, the inventor of Kafka, who's one of the guys over at Confluent, the Kafka guys right now. It's a pretty good read. You know, he's a good writer, and it's a good read. So anyway, Hbase is a NoSQL database system. Remember HDFS, random reads, random writes, forget it. Hbase, you give up SQL, it's not transactional, it's not even structured the way relational databases are, but it is a key value store of massive scale, right? So that you can write records into a table and you can read records and you can read any record you want according to key. So you can write a record in 4 milliseconds, read a record in 10 milliseconds. And you can have millions of, many readers and writers all doing that concurrently, randomly. So it's, it's completely the other end of the things in terms of I/O patterns, I/O capabilities than HDFS. But analytic queries, when you want to read all the data and do a processing job on all the data and do some summary kind of work, it underperforms against HDFS. So HDFS is stronger at sequential consumption of a large amount of data, right? And HDFS is much, much stronger at random access, random read and writes of individual elements of data. NoSQL data store, right? It's not ACID compliant. It's not SQL at all. It's got primitive I/O operations, right? You may or may not choose to use Hbase on a given cluster, right? Kudu is yet another data store, right? So Kudu, you create a table definition like a SQL table with rows and with columns and data types on columns of a table, right? And it's another data store. It doesn't use HDFS under the hood. It uses file system directly on the workers across the cluster. And its I/O patterns are, it's not as fast as HDFS at sequential throughput consumption of all the data, right? But it's much faster than Hbase at sequential access. And it's not as fast as Hbase at random reads and updates of individual records, but it's much faster than HDFS. So it's somewhere between the two. Some compromise in terms of, and so it really becomes a matter of what are the needs at the time of a data store. You have a choice of data stores now, right, with which to store data at scale in your cluster. And you can mix and match. You can have all three of those deployed on the same cluster if you wish, depending on your needs. Like what? Kudu, well, drill is kind of like, we're going to talk about Impala in a minute. So Kudu is actually an actual data store. Right. So Kudu is a data store in its own right, okay? So you're storing data in this data storage of a file system or a NoSQL database system or this Kudu system. Yes? So Kudu is in your cluster. There are daemons that make up Kudu that are part of your cluster. It's just an alternative storage technology to HDFS. Right, for example. Does that make sense? So if I told you on some server, this stuff is in a file and this stuff is in Oracle, right? So those are two very different ways of storing your data, right? And they have implications in terms of access that you can do and what you can put in there and kinds of latencies you can expect, right? That's what this is. It's a data store. Well, Hbase is implemented over HDFS, but it is characteristically very different, composed of all these daemons that organize, do a lot of fancy work on the file system to do their work. In the same way that Oracle is built on a file system, and you wouldn't say, oh, well, if it got stuff in a file system and stuff in Oracle, you wouldn't say, well, the Oracle stuff is in the file system too, right? No, it isn't. It's in Oracle. You have to use Oracle to get it, right? You're going to use Oracle. In the same way, you would use Hbase to read and write data. You would use Kudu to read and write data. You would use HDFS to read and write data. Hbase is like a cluster of a bunch of smart database servers that are juggling all kinds of files of their own with their own internal format to give you this abstraction of a random access table. So it's offering up to you this big table with a billion rows that you can read and write any row you want. And under the hood, it's juggling all kinds of its own format HDFS files on its own with a lot of memory caching on its own. Yes?
So the concept of the block placement policy, for example, only applies to HDFS.
Block placement policy is a property of HDFS. Hbase leverages that to gain efficiencies in a suitable way. There's a synergy in terms of the way they operate. But yeah, that block placement, we were looking at Hadoop core a minute ago, and now we're on to all these other things that add out to the Hadoop ecosystem. Right? Yes? So Kudu doesn't use HDFS. It uses files directly on the it has its own daemons that reads and writes its own files on disk on all the slave machines. And then it provides basically this database table type abstraction automatically all the time. And it provides access patterns of performance. Like I said, it's a compromise in terms of random access, speed of random access and speed of sequential throughput of all the data. Yes?
If it has no relationship with Hadoop, then why is it here?
No relationship with Hadoop. So Kudu operates on a Hadoop cluster, right? So let's put it, no relationship with Hadoop. Yes, it is related with Hadoop. In other words, you deploy Kudu in a Hadoop cluster, right? Again, what does Hadoop mean? Is it to mean Hadoop core or Hadoop ecosystem? Kudu is part of the Hadoop ecosystem and is not part of Hadoop core. But a MapReduce program can read and write Kudu. Right. Right. So MapReduce program can read and write Kudu. Kudu runs on its own. It's its own deployed set of components. So Yarn is more about the scheduling of ephemeral programs and not services that sit and remain on an ongoing basis in the system. That's what Yarn is more about. And so when you want to permanently deploy a set of services or daemons across your cluster, then you move into your own system. And that's what Kudu is. Yeah.
What do you mean by ecosystem? What the criteria to consider if technology or tool is part of it?
The question is, what do I mean by ecosystem? And hold that question. Okay. So Hive, remember we're stuck with MapReduce, but golly gee, writing a map function and a reduce function, and even worse, having to write them in Java, which has a lot of ceremony, shall we say, to write a Java program, right? So is really heinous, right? It's a lot of work. So the guys over at Facebook developed this abstraction called Hive, which lets you write what looks like a SQL statement, but really drives down into MapReduce. So Hive it's not SQL, it's MapReduce for people who know SQL. It translates your Hive statement into MapReduce for runtime. Or Spark. We're going to be mentioning Spark. By the way, I notice it's 3:10 and I'm about halfway through. So I'm going to have to start blasting, start picking up my pace. I do this all the time. I go over all the time. So Pig is a data flow language that translates immutable data set, transforms to another, transforms to another, transforms to another. That's the abstraction for the programmer. And then it translates into MapReduce to runtime. Or Spark. Nowadays, they call that project Spork, the translation of Pig into Spark. Impala is the one like Drill. It's a purpose-built, written in C++, native code, all kinds of accelerations, right? That does high-speed analytic queries on data in your Hadoop cluster. It really follows on exactly what happened with Drill at Google. It's like, well, gee, we've got all these cool things that we can do, a lot of data, a lot of processing, a lot of interesting things. Now can we do faster queries? Can we purpose-build something for that? Right, and the guy who was, the guy at Cloudera who built the team to build Impala was at Google on Drill, and he used those insights to help design Impala. It's not a Drill lookalike, but But it's a high speed, and it's faster. Exactly. There's no one number, but depending on what you're doing, it could be 100 times faster. It's for analysts doing ad hoc analytic queries is the general use case. Yes. Yes.
So Impala, it leverages an abstraction over.
It is a processing. So it reads HDFS, it reads Kudu, it reads Hbase, it reads any of those. You've got data store, choice of data store, choice of processing layer, mix and match any way you want. Right? Columnar storage is a file format like Parquet. That's storage. But it does acceleration with all kinds of internal optimizations, direct reads, C++ native code, local caching, all kinds of things. It's a whole series of things that it does to gain efficiencies. Okay, and more, right? File formats, Avro and Parquet, efficient storage of structured data, efficient columnar storage of structured data. Workflow, Uzi, right? That stitches together tasks, copy some files, run a MapReduce job, run a Hive query, do a Sqoop import, join that data with another Hive query, do another copy some files over, do another Sqoop export to an ETL to a warehouse, stitch that together in one flow, write an Uzi workflow to do that, schedule that to run four times a week. Right? Security. Sentry and record service. These are different layers of security, which is a pretty complicated topic, but having to do with guaranteed authentication of the users in the system and then authorization of which data they can see and not see and be aware of and not aware of. Record service is the more extended one now that is at an abstraction layer that then basically an abstraction layer between all access of all tools to your system. Right, so it's really the more, and it builds on to Sentry. You notice that it's not an Apache project at this time. It is open source, it is Apache licensed. It's an example of one of the projects that Cloudera has written and that at some point will contribute it to the Apache Software Foundation, like we have done with Flume and with Sqoop and with Impala already. Yes?
Are there any applications of web pages that record any intrusions into Hadoop databases?
Intrusions into Hadoop database? I don't know of any such thing. That's an interesting question. The question is, is there a record of intrusions in Hadoop clusters? Beats me. But certainly security is a concern in the enterprise. I mean, my employer is concerned with exploiting larger and larger amounts of data in the enterprise. So you've got to be, basically, the open source code kids who like to play on Apache can do all kind of fun things, but you need some grown-ups in the room, and so like a lot of focus on this is part of what my employer is about. And we have demonstrated PCI compliant Hadoop clusters along with MasterCard. We actually did publish a test, a proof of PCI compliance with MasterCard. So we definitely care about that. And then machine learning in MapReduce. See, I put this on the end. Perl Mahout. Mahout is machine learning in MapReduce, and it's really falling behind. It's really beat out by Spark. So it's pretty much deprecated. Even the engineers on MapReduce have moved on to Spark now, right? But anyway, what about Spark, right? So Spark is a project, came from here, the AMP Lab, they published this paper out of AMP Lab in 2009. And what it basically does is it addresses the clear pain points of MapReduce, and I would say very usefully and elegantly. They did a lot of good work, right? But what it fundamentally is I would say it's next generation from MapReduce. At bottom, under the covers, it is MapReduce. It is doing the same thing, right? So that's why I wanted to spend a lot of time with you on that, kind of understand what we're dealing with. But I will mention that it does add this new thing called micro batches there's a sub-project called Spark Streaming that will absorb data. You say your Flume ingest. And by the way, Kafka and Flume, I didn't mention, they can be used together. We call those solutions FLOFKA solutions, where you use the Kafka reliability and capacity together with the pre-written code already available in Flume to get like a good solid ingest pipeline, right? So you can ingest data and then every second stop and run a batch on that 1 second's worth of data. So-called micro batches. That's Hadoop, that's Spark Streaming, a sub-project of Spark. Okay, but fundamentally, it's like MapReduce. It's processing MapReduce volume. It's using scale out. It's using stateless functions, right? It provides reliability, machine failure, doesn't stop the program from running, will still run to completion. You're using stateless functions. There is still shuffle. It's still expensive. You use shuffle to do joins, aggregation, sorting. All those rely on shuffle to do those things at scale with massive amounts of data. It does not have shared state among all the processes the same way as MapReduce. It runs under Yarn the same way as MapReduce. So the cluster runs at any given time, any kind of mix of MapReduce and Spark programs going all at the same time in the cluster under Yarn, right? But improvements, the API, that's a Spark program for that MapReduce program. It's a much more elegant, clean API. Some people say that it's pig done right. The paradigm of pig, of a data set transformed to another, to another, to another, is the thought process. That's the same thing. Pig works the same way. People say it's pig done right. Actually, the syntax of pig is pretty sloppy, which is probably appropriate for a project named Pig, right? But anyway, but Spark is this clean, elegant API, and what that means is that engineers can very quickly get to more powerful programs much more quickly. And so that a host of more powerful libraries and sub-projects have just really blossomed off of this basically clean API that it produces. And first-class APIs in Scala, Java, Python, and R, any of those, pick your language, right? R was the latecomer, but those are all APIs in Spark. It's got an interactive shell, which is great. You can open up a shell and have at your command access to your big cluster and do interactive work with the cluster to sort of explore it. Rather than having to write a program, compile it, run it in batch, come back, look at it, that interactive shell is very, very useful for exploratory work. Very, very big, very useful. And then this project called Spark SQL adds the idea of adding clear structure, of a table-like row structure to your data, which again enhances usability. It makes it more clear what you're working with when you're running a program, right? So anyway, runtime. Back to MapReduce chaining. This could be a Spark program, but what Spark does is, instead of stopping, well, let me say a couple things. So these functions, right, rather than running as separately scheduled tasks that are independently scheduled on the cluster, when the Spark program spins up, it commits these processes across the workers on the cluster called executors or executors, right? And those then run these same operations as tasks within that process rather than as separate processes. So rather than having 20,000 little short-lived processes, right, you have 20 or 200 longer-lived processes that run 20,000 tasks within those processes. So because those processes hang around for the life of your app, they can buffer data in memory in those processes, right? See, MapReduce is from 15 years ago. You didn't have the kind of memory, 192 terabytes and up, like you do now, right? So you can commit memory, and you can buffer stuff in memory. So these are tasks, not processes. You can do caching in memory. So then you can do exchange of data between processes, memory to memory, exchange of data between different processes without I/O, right? So like this, and instead of some lockdown to MapReduce write, Spark is arbitrarily long chain of these functions stitched together, right? So by eliminating I/O here, a write is slow, a read is slow, and then improving the I/O of shuffle, where write and read are still slow, but you're still doing, when you do less write and read, cache as much as you can and write when you have to because data forces you to. You gain improvements. And the more complex the algorithm, the longer it is, the more Spark runs away from MapReduce in terms of performance. If all you're doing is reading a record, scrubbing it, and writing it, Spark is probably not that much different from MapReduce, right? But if your algorithm is more complex and more, you have to chain together more, then it gets better and better and better. Especially iterative algorithms where you crawl over the data again and again and again. Guess what kinds of algorithms are iterative? Machine learning algorithms. Approximate a model to a data set, crawl over the data and improve it. Crawl over the data and improve it. Crawl over the data and improve it until you're happy, right? That's why Spark, machine learning in MapReduce in Spark is a real winner. That's why it shines. That's why this. This is from the front page of the spark.apache.org website. I feel compelled to point this out. This is on the front page of the spark.apache.org. Hadoop Spark, right? Well, you know, so Hadoop is 100 times faster than, Spark is 100 times faster than on Hadoop. On a particular algorithm, logistic regression, which is an iterative algorithm. But just be clear, what do you mean by Hadoop? See, if Hadoop means Hadoop core, fine, right? But if you, by now I hope you realize that there's no such thing today as a Hadoop cluster that runs Hadoop core that doesn't also run probably about 24 additional projects that flesh out the feature set of your Hadoop cluster. A Hadoop cluster is not running Hadoop core alone. It's running a combination of things. And the ones that I've listed are only some of them. You know, there are other options. Right, and there's an evolving, you know, plug, mix and match, find the best of breed for something you want to do, right? So if you, but I mean, taken on the face, people say, well, Spark's a Hadoop killer. Well, what do you mean by Hadoop, right? So I would say that this is almost like saying electric engines replace automobiles, right? So it's not a paired comparison. Yes, electric engines, electric motors may replace combustion engines in use in automobiles, right? Or put it another way, just be clear on what you mean when you write that, when you say that. Okay, good. So commercial message number 1. All this stuff, right? That's a lot to manage. But you want some combination of those and maybe some other things, right? We are offering Cloudera Manager. Yes, Cloudera Manager is a free software component that will install, deploy, manage, upgrade, start and stop a cluster of 10 or 100 or 1,000 machines running any combination of those things and more. It's a coherent it's a piece of software that coherently will manage your cluster, having all that stuff. Cloudera Director will do it on the cloud. Into commercial. Machine learning. Right? So who said they could list and explain 5 or 6 machine learning algorithms? Okay, so basically you're looking at supervised and unsupervised learning, right? And I'll just list some of them: regression, logistic regression, classifiers, collaborative filters, clustering. Those are examples, right? So regression, see, that looks like plain old statistics, but yeah, that's machine learning. Fit a line, right? Once you fit this line, then you can say, well, for some new record, if I know an annual income, I could estimate what a monthly fee would be, an acceptable monthly fee is. So the system has learned to predict an acceptable monthly fee for a new customer given their annual income. Linear regression. Logistic regression, that algorithm that Spark says it wins on. Where you're predicting is a 0 or a 1. They cancel or they don't cancel. So say you're predicting a continuous number or a binary number or a classifier, a categorical variable. look at an image, tell me if it's a cat or a table, or a house, or a dog, or a, you know. So you're predicting a continuous, or a binary, or categorical. Those are all supervised learning. You give me a bunch of data that's already properly labeled, and I'll learn to do no more labeling. Classifiers and regression are of a piece, really, in terms of what they do. Collaborative filters is unsupervised. It's like, given these preferences of these users for these movies, right? Guess what their preferences would be in the null values, so they can use that to offer things to them that they might like, right? There's no definite right answer. There's no known answer. It's not pre-labeled. You don't know what their preferences is for them. You're trying to take your best fit to what's there. That's unsupervised, right? Clustering. Given some data, find 3 canonical groups that represent that data in simple terms, right? So you can think of it as segmentation, or really use segmentation or feature reduction sometimes, right? There's no definite right answer. You don't even know if the right answer is definitely 3, right? But you're trying to come up with, right? Those are unsupervised, regression, collaborative filter, and clustering or machine learning. Believe it or not, really a whole host of machine learning algorithms come under the head of those things. Those things, together with, you know, some basic statistical examination of data, looking at correlations and things, and together with techniques for optimization, right? Now, there are different ways to do classifiers. There's Bayesian, where you basically count frequencies and then you use that to deliver a weight, right? If 4 out of 10 emails you've seen are spam, then my guess is a 0.4 probability the next email is spam. Extend that, right? Or you can do decision trees, where you build out, you know, what splits up the data set, and, you know. There's a lot of ways to do classifiers, but classifiers is a whole host of algorithms that do that. So the deliverables of these sorts of these things are what you're looking at, right? Regression, logistic regression, classifiers, collaborative filters, clustering. Spark, here on the, if you just click around on Spark, you go to the programming guides, has this project called MLlib, that has implementations at scale in the cluster, implementations of those things. Not every algorithm works at scale. You remember, you have to shoehorn your problem into essentially MapReduce. Spark is giving algorithms that do shoehorn into the constraints of that runtime framework. Very usable, very usable. If you know scikit-learn from Python, a lot of the pipeline building sort of imitates that. Very cool. The future. Commercial message. What we're looking at is more DS teams where you've got an organization with a growing set of different teams that want to get into the data of growing amounts of data at scale that are operating at scale in the cluster, but you have security constraints on who can see what, right? But you want these teams to be able to do work on the data at scale in the cluster. You want different teams to collaborate. You want them to be able to share repeatable work, a la notebooks, right? With other people who can check their work and verify what they're doing. And you've got teams today that some of them, that not all the algorithms that you run are all in Spark, in MLlib. A lot of things you operate with data at more modest scale, and you use something like Pandas and scikit-learn in Python, or you use H2O, or there's a whole bunch of R packages. So their teams have these sort of favored packages and tools and techniques that they're used to using when working with data that's not big data, and they want to operate with that. And they even want to run different versions of Python, 2.7, 3.0, depending on what packages they want to run, right? So that's the practical concern, right? And so Cloudera Data Science Workbench, this is my advertisement. This went GA, general availability, last week. There's a blog about it today. What it does is it uses containers to set up for a given team a project with the install of the software they want to use, with the versions that they want to use, to host all their data just by going for a browser against the cluster, and they can operate, one team can operate on their secured available set of data using their tools they want to use. They can use R or Python or Scala. They get these notebook style results where scripts that are maintained as projects against the data get rendered, with sort of markdown and with visualizations and everything, and they can share at will, and it's all secured, right? So what we're looking at is the practical concerns of getting data science teams applying these techniques in this, basically this reservoir, the concern of getting practical people to practically use that in this big lake of data. End of commercial. Bleeding edge, deep learning, right? Hot topic today. Another way of doing classifiers is just there's different algorithms for classifiers like Bayesian or decision tree. Deep learning. Deep learning says, well, you build these processes that take inputs, and then it sends out signal with different weights to these other processes that they're simulating neurons, right? And that in a simplified way, that then take those weights and compose those to another set of weights to do it again, to do it again, to do it again. And what this really does is, and the main thing about deep learning is that they found a way using differential equations. There's this thing called back propagation, where they're figuring out what are the weights going to be, what should the weights be, right? And where it's shining is that when you have high dimensional inputs, so in other words, instead of having 8 inputs, you have like every pixel on an image. So, you can have, you could literally be like a video frame from an image, right? And what Google did, they took a frame from YouTube videos and they took 100 million videos, took a frame from them. So each of these inputs are these, and the number of layers here could be, instead of being, so-called 3 hidden layers, they have like 50, 60 hidden layers, right? And the number of simple categories, so it's a cat, it's a house, it's a table, right? It's a dog, right? Coming out, spitting out here on this can be 10,000, right? So what you got is stuff that, what it's requiring now today is stuff that is not so much data intensive, which it is, but also computationally intensive, right? So there's a lot of calculation, and there is a concern of shared state. Right? In other words, what's going on in this model? What's this network telling you, right? And so it's a concern. So Spark ML Live does not implement deep learning, but there are choices for implementing deep learning. Big DL is an additional project that will add deep learning to Spark. So does Caffe from here, Berkeley, TensorFlow from Google, DL4J, this company called SkyMind. It's a question of where is deep learning going to fit into Hadoop, if you want to see what I mean by Hadoop ecosystem now. Who's going to bring deep learning? Those are all possible. And by the way, Cloudera, Data Science Workbench, can drag any of those in. You can use any of them. It's a question of where's deep learning going to go in this particular ecosystem? But the road ahead really says this, right? It is a truism. Organizations today have unexploited value in data. Data is a huge asset. There is more to get out of the data they already have. 90% of the data that will exist at the end of this decade has yet to exist. Open source is here to stay. It looks like Hadoop is going to keep the likes of me entertained and employed for quite some time, right? That's really what I think the future is. This is what we think it is, and of course, what Cloudera thinks. I'll just offer, a personal opinion. Whether you call it Hadoop in the end, or whether it evolves into something where it's called the big data platform, doesn't matter to me. But these origins will just keep evolving and going. And that's it for me. Thank you. Sorry for going over here.